Lesson 22, Bisectors and Triangles. Your objectives are to prove and apply properties of perpendicular bisectors of a triangle and to prove and apply properties of angle bisectors in a triangle. The vocabulary for this lesson are concurrent, point of concurrency, circumcenter of a triangle, circumscribed, incenter of a triangle, and inscribed. Since a triangle has three sides, it has three perpendicular bisectors. Remember that a perpendicular bisector is a line or a segment that bisects another segment. When you construct the perpendicular bisectors, you'll find that they have an interesting property. The perpendicular bisector of a side of a triangle does not always pass through the opposite vertex. When three or more lines intersect at one point, the lines are said to be concurrent. So any three lines that intersect at one point are concurrent lines. The point of concurrency is the point where they intersect. In a construction, you see that three perpendicular bisectors of a triangle are concurrent. They will intersect. The point of concurrency is the circumcenter of the triangle. This gives us the circumcenter theorem, which states the circumcenter of a triangle is equidistant from the vertices of the triangle. Or in this case, PA equals PB, which also equals PC. Let's take a look at this triangle. The red line segments are the perpendicular bisectors. They are perpendicular to the sides of the triangle, and they bisect each side. The blue lines are taking the circumcenter of the triangle and moving and connecting it to the vertices of the triangle. These segments, the blue ones, are the ones that are equidistant or congruent. The circumcenter can be inside the triangle, outside the triangle, or on the triangle. The three cases I want you to look at are an acute triangle, where the circumcenter P is inside the triangle. We have the obtuse triangle, where the circumcenter will be outside the triangle, and a right triangle where it is on the triangle. The circumcenter of ABC is in the center of its circumscribed circle. A circle that contains all the vertices of a polygon is circumscribed about the polygon. So I have triangle ABC, and I have a circle around it, and the vertices are on the circle. The circumcenter of triangle ABC also happens to be the center of the circle in which it is circumscribed. Let's look at some examples. In our picture here, we say that DG, EG, and FG are the perpendicular bisectors of triangle ABC. We have our perpendicular signs here, and they are bisecting each side or each segment. We want to find the length of GC, this one right here. Since G is the circumcenter of ABC, by the circumcenter theorem, G is equidistant from the vertices from ABC. So AG, BG, and CG would all be the same. So using the circumcenter theorem, GC is equal to GB. If we substitute in 3.14 for GB, we get that GC is equal to 13.4 because we know that BG is 13.4. Let's look at another example. We want to find the circumcenter of a triangle. Find the circumcenter of triangle AHJK with vertices H0, 0, J10, 0, and K0, 6. Step 1 will be to graph the triangle. So here we have our triangle graphed. This would be H, this would be K, and this is J. Step 2, we want to find equations for two perpendicular bisectors. Since two sides of the triangle lie along the axes, use the graph to find the perpendicular bisectors of these two sides. The perpendicular bisector of HJ is x equals 5, and the perpendicular bisector of HK is y equals 3. Step 3, we're going to find the intersection of the two equations. The lines x equals 5 and y equals 3 intersect at the point 5, 3. That's the circumcenter of AHJK. Make sure that when you look at this picture you understand the reason we chose y equals 3 is that the midpoint of this segment is at 3, 0, 3. The midpoint between 0 and 10 would be at 5. So this would be the points where they would be perpendicular. Then if we draw those two lines, a vertical line and a horizontal line, we can find the intersection point. A triangle has 3 angles, so it has 3 angle bisectors. The angle bisectors of a triangle are also concurrent. This point of concurrency is the incenter of the triangle. This gives us the incenter theorem in a nice picture to understand what we're talking about. The incenter of a triangle is equidistant from the sides of the triangle. Remember before we had the circumcenter. It was equidistant from the vertices of the triangle. The incenter is equidistant from the sides, so it must be here inside this. So if we look, we have this angle bisector here, bisecting A. If it continued on, it would just keep going over here. C would cross and go over this way. The bisector for B would keep on going somewhere down here. But what we've shown you here in blue are the perpendicular bisectors. You can look at them and eyeball them and see that PX equals PY equals PZ. So if you cut the angles in half, you end up with a point, the incenter, which is equidistant from the sides. Unlike the circumcenter, the incenter is always inside the triangle. With an acute triangle, it's inside. An obtuse triangle, it's still inside. And a right triangle, it is inside the triangle. The incenter is the center of the triangle's inscribed circle. A circle inscribed in a polygon intersects each line that contains a side of the polygon at exactly one point. So even though the red is contained inside of this black triangle, you would have one point shared with the side and the circle on each side. P, the incenter, is the center of this circle. So circumscribed means the circle goes around the polygon. Inscribed means the circle is inside the polygon. Let's look at example 3a and use properties of angle bisectors. MP and LP are angle bisectors of triangle LMN. Find the distance from P to MN. So we want P and how far it is to get to MN. P is the incenter of triangle LMN. By the incenter theorem, P is equidistant from the sides of LMN. The distance from P to LM is 5, so the distance from P to MN is also 5. Let's look at another one. MP and LP are angle bisectors of triangle LMN. Find the measure of PMN. So we want to know the measure of PMN. So this angle right here. First of all, PL is the bisector of MLN. So the measure of MLN equals 2 times PLN. We'll substitute 50 for PLN. The measure of angle MLN equals 2 times 50, which is 100 degrees. Remember what we said, we look at the picture, not at the, we look at the numbers, not the picture. The triangle sum theorem lets us say that the measure of MLN plus LMNM plus LMN equals 180 degrees because the measures of a triangle of the angles is always 180. We substitute the given values that we have. 100 plus 20 equals 100 and plus LMN equals 180. Subtract 120 from both sides and we have the measure of LMN is 60 degrees. So that's LMN. PM is the bisector of angle LMN. So the angle PMN equals 1/2 of LMN. Substitute 60 for LMN. So the measure of PMN equals 1/2 of 60, which is 30 degrees. Now you try. And a second page. And a third. Make sure you answer these. Bring any questions you have to class.